Hello, and welcome to Lecture 3, covering Section 2.5 from Survey 10th edition, in this calculus-based introduction to physics. In this chapter, we're just covering a single section, as you can see, and the topic is average and instantaneous acceleration. So we want to relate average acceleration to change in velocity, recognize the tangent of a velocity versus time graph as the instantaneous acceleration, and that the derivative of a velocity function is an acceleration function. Okay? So this is going to cap off our discussion of kinematics, because once we get to acceleration, we've covered the big ideas of kinematics: position, velocity, and acceleration. And we'll soon see that acceleration is of particular importance because of its relationship to force with Newton's second law. But before we get to that, let's see how we work with acceleration, especially in relation to position and velocity. All right, so a term I want to get out of the way, although we won't be really putting it to full use until later in the course, is something called a non-inertial reference frame. It's simply a location that is accelerating. All right? So let me elaborate on that a bit. So a reference frame is just a location where measurements are made. So you could say a non-inertial location, but we say a non-inertial reference frame. It's just a more technical term for locale or location. Okay? And on the other hand, an inertial reference frame is a location at rest or at constant velocity. So you can see then that that term inertial versus non-inertial means either accelerating or not accelerating. Okay? So, what the heck is acceleration itself? Well, acceleration is just a change in velocity per time, just like velocity is a change in position per time. Okay? So there you go. We'll, of course, define it again in the equation form. Instantaneous acceleration is the tangent line of one point on a velocity curve, whereas average acceleration is the secant line between 2 points on a velocity curve. I'll show you that in just a minute. Okay? So let's look at our equations. Our equation for average and instantaneous acceleration. Okay? Average, we can have the subscript, or we can just use a bar over it, as we can always denote an average with a bar above the letter. Delta V over delta T. Okay? Whereas instantaneous acceleration is the limit of delta T as it goes to 0, because we're getting a closer and closer approximation to a true exact moment in time, an infinitesimal small change in time. This then by definition changes to a derivative. We can then represent that derivative like this, because this is v for velocity. That dot represents one time derivative. Or we can write it as the second derivative of position, right? Because if acceleration is the time derivative of velocity and velocity is the derivative of position, then of course acceleration must be the second time derivative of position, which would be x double dot if we're using a very shortened notation. So let me show you a graph to elaborate on the idea of tangent lines and secant lines. Okay, right over here. So we can see, by zooming in a bit, that we can look at a single point at t naught, and this purple tangent line is the instantaneous acceleration at t equals t naught, at that particular time. And of course, this graph is velocity versus time. So then any curve on this graph, any slope on this graph, is by definition an acceleration. It has the units of acceleration, because the units of acceleration must be meter per second, or just meter per second squared. Right? Rise over run. On the other hand, secant line connects 2 points. So this is the average between t1 and t2 is whatever this slope is here. Okay? So that's the idea of secant versus tangent. All right? All right. So then what's going on down here? Well, we could have included this formula right here in the previous section where we define velocity, but it makes sense to kind of put these side by side. And as I said, this represents the culmination of introducing the key ideas of kinematics. So this is a culminating idea. Basically what it's saying is that velocity is the antiderivative of acceleration and position is the antiderivative of velocity. Or put a different way, change in velocity is the definite integral of acceleration. Change in position is the definite integral of velocity, both with respect to time. Okay? So can you write this as indefinite integrals and have a constant of integration? Absolutely. When you solve for that constant of integration, you're always going to find that it is the initial condition. In the case of doing the integral for velocity, doing the integral of acceleration for velocity, you'll find that constant of integration will always be your initial velocity. Likewise, your constant of integration going from velocity to position will always be your initial position. Okay? So what does this look like graphically? Well, just defined that v minus v naught is delta v, just for shorthand, and x minus x naught is delta x. Well, then graphically, here we have velocity versus time, just like with the graph where I drew tangent lines and secant lines, but here I've only labeled a t naught and a t. Okay, so now I'm going to look at the area under the curve. So this purple shaded area is change in position. The units are meters. The actual magnitude of this area, it's a scalar after all, area is a scalar, is change in position. Okay? Likewise, if you look at a graph of acceleration versus time, between two times, t naught and t, and shade some area under that curve, that green shaded area is change in velocity. It's not final velocity. Its units are meters per second. It's the change in velocity. Okay? So that's how calculus relates to velocity and acceleration. We'll be doing that more, relating calculus to velocity and acceleration, certainly in practice with examples, and I'll be doing it again in the next lecture to introduce a set of equations which are called the kinematic equations. Not because they're the only equations in kinematics, but they're particular equations that get used a lot, so they get that special name. All right, so we're going to look at some types of problems. We're going to look at three types: simple problems that involve finding an average acceleration, problems that involve taking derivatives of position and velocity functions in order to find acceleration functions and sometimes evaluate those functions. And finally, the third type, problems that involve taking antiderivatives of acceleration functions in order to find velocity or position functions. This type of problem requires initial velocity or position to solve. So you can see there's a key difference between type 1 and type 2. Okay? Type 2 and type 3. Type 3 requires extra information. So in other words, going from acceleration to velocity and position, taking antiderivatives is inherently more complex, not much more, but does at least require more information up front to actually solve. Whereas just taking derivatives, you don't need that extra information. Okay? So let's look at our first example, a nice simple one with average acceleration. A particle has a velocity of 23.2 meters per second at t equals 13 seconds and negative 11.9 meters per second at t equals 20.5 seconds. What is the average acceleration during this elapsed time? So it's definitely a plug and chug problem. I did hopefully make it interesting by having the acceleration go from positive to negative. Okay, so by definition, average velocity is just delta v over delta x. Delta v is v final minus v initial, just like delta x that should be delta t. I don't know why I wrote that. That's a typo right there. That needs to be fixed. That should be delta t. All right, so I'll take note of that. Please take note that this is a stupid typo. That should be delta t. As you can see here, it's correctly written as t final minus t initial. Okay, I don't know where the x came from. We'll just say it was a badly written t and I read it wrong. Okay, and as we move on, then we obviously just put in the final velocity. That's the negative one. The initial one is positive. So you can see as you take the delta, it's actually just going to be a larger negative. All right, and so you're further from 0. And then our time is obviously going to have to be positive. You can't have negative time. And there we have it. Our average acceleration between those times is given with those velocities is negative 4.68 meters per second. It's a negative acceleration. Why? Well, because it took a positive velocity and made it negative. In other words, if the velocity was 23.2 to the right and it ended up with negative 11.9, which would be like 11.9 meters per second to the left, then the acceleration is also to the left, the negative direction. Okay, let's look at example 2. All right, so here we're asked, so the x velocity, vx, of a car at any time t is given by the equation. Okay, so here we're given an equation for v sub x, 60 meters per second plus 0.5 meters per second cubed times t squared. Okay, and then in part A, we're just asked what is the change in vx over the interval t1 to t2. T1 defined as 1 second, t2 is 3. Okay, so something to note here in this problem, we're specifically defining the axis that it's on, all right? Whereas in the previous problem, it wasn't stated. Excuse me. That's just, and I want to always show you different notation, different way these problems might be worded. Furthermore, our velocity function specifically has the correct units on each term, because each term has to have units in meters per second. Thus, this coefficient here, this 0.5, must have units of meters per second cubed. So when we multiply by t squared, which would be seconds squared, we cancel out the appropriate number of seconds to be left with just meters per second. Okay? All right, so let's go ahead and then just solve the problem. So we'll plug in v final, evaluated at 3, because we were told that that was t2, and then, which is the same as t final. And then we're going to plug in the function, evaluated at 1 second. Make sure to distribute the negative. Our 60s cancel. So then we're just left with 4 meters per second, because we just have 0.5 times 3 squared, which is 4.5, and then we're subtracting 0.5 times 1 squared, which is just 0.5, so 4.5 minus 0.5 is 4. All right, so that's the change in velocity given that function over the specified time interval. And then we're asked, what is the average acceleration? Well, since we already have the delta v, which we kind of separately solved for, then we just divide by the delta t, which is just 2, of course, in this problem. And so then we find that the average acceleration is 2 meters per second squared. Okay, so straightforward. We won't spend any more time on that. Let's look at another example. The x velocity, okay, so kind of specified the same way with the same notation, of a car at any time t is given by, well, same equation, okay? Derive an expression for the instantaneous x acceleration as a function of time and use it to find acceleration at 1 second and 3 seconds respectively. Oh, okay. So the only difference, as denoted by the color, is we're not finding average. We're finding two instantaneous accelerations. And we're finding them to kind of sandwich in the average that we found. Because we're finding it at the beginning of the interval that in the previous example we found the average for, and at the end of the interval from the previous problem. Okay? All right, so then we're just going to use the acceleration. So now as a function, I'm just going to take the derivative, follow the rules of derivatives for polynomials. When I take the derivative of a constant, it goes to 0. When I take the derivative of this expression, the 2 goes in front. 2 times 0.5 is 1. So then we're just left with an acceleration of 1 meter per second cubed times t. Check that the units work out here. All right. So then if we evaluate that at t equals 1 second, we just get 1 meter per second squared. And if we evaluate that t equals 3 seconds, we just get 3. Because essentially our acceleration here is a linear acceleration that has a slope of 1. That's what this is telling us. And if you look at it, well, if you take the average of 1 and 3, you get 2. But that should make sense because since acceleration is linear, finding the average will give you something exactly in the middle. If the acceleration was, say, parabolic, it wouldn't necessarily give us something exactly in the middle, right? Okay. All right, so now let's look at 4. Notice the color here. So we should expect the use of antiderivatives in this one. But otherwise it's the same problem. The setup is the same. X velocity, v sub x, all right, same function, right? It's a car again, vroom, vroom. All right, and here, however, right away I'm giving you extra information. I specify at x equals 0, t equals 0, all right? All right, or in other words, probably better to say x equals 0 at t equals 0, because it's not that t is dependent on x, it's, of course, x is dependent on t. Then where is the car located at the moment that the acceleration is 10 meters per second squared? Okay, interesting. So we can definitely find out what that moment is, just kind of by thinking about it, because we know that it goes up 1 meters per second squared per second. So we should probably expect that to give us 10. Let's prove it. All right, so use a equals as our function from the previous one. Our function for acceleration, okay? Our time-dependent function for acceleration. Define t at a equals 10. All right, so that's it. Literally just 10 divided by 1. Which of course gives us 10 seconds. All right, so check, got that. Okay. Now what do we do with that information? Well, we need a position function. Oh, okay. Well, to get a position function, we'd better do an integral. Okay, so for position, we're going to use our integral definition, and we're going to go from the given velocity function and get our change in acceleration. Okay, but look, our x naught, because x at t equals 0 is, in other words, x naught, is given to us. We're told it's 0. All right, so there we go. Okay, so that means we can clean this up a bit. All right, notice the left-hand side of the equation just simplified to x, because x naught's gone. It was 0 after all. And then putting the function form of velocity in, 60 plus 0.5 meters per second cubed times t squared. Of course, the units on 60 are meters per second. Okay, there we go, evaluated dt. It's our differential. We're going to integrate from 0 to t. Notice that this is a definite integral, but with a variable at one of the limits of integration rather than a value, but we just plug it in like we would any value. All right, and so when we do antiderivatives, a constant becomes that constant times the variable to the first power. So essentially the constant becomes a coefficient. And then we have to divide by the higher polynomial with the antiderivative. So 2 goes up to 3, and then 3 goes into the denominator. Well, 1/2 times 1/3 is 1/6. That's where that comes from. All right? Still, same units on there, and then times t cubed, because when you do antiderivatives, polynomials increase in power. All right, so now we just need to evaluate that at 10 seconds. All right, so we plug a 10 in there, we plug a 10 in there. All right, and what do we get? 770 meters. Okay, so it was a two-step process where we had to find a particular point in time and then do an antiderivative and then plug that time in. Maybe that's 3 steps, but you get the idea, okay? Let's do one more antiderivative problem, but first, a concept question. For each of the curves, use your understanding of position, velocity, and speed to answer the questions in the following table. Also note that the variable x stands for distance, okay? So let's move right along. So all I'm doing here is just drawing some examples of velocities. Here's some velocity at point 1 and some velocity at point 2 on the first curve. Likewise in the second curve, likewise in the third curve, and likewise in the fourth. That's just going to help collect our thoughts. Obviously, all those green lines are tangent lines. They're instantaneous velocities. Okay? All right. So no acceleration directly displayed, but there is acceleration indirectly displayed. More on that in just a minute. And maybe you know what I'm hinting at. So first of all, is the slope of the x-graph positive or negative? Well, in A and B, it's positive because all the slopes go up. Okay? In C and D, all the slopes are negative. Okay? So when it says the slope, it means any given slope. Okay? Good. So 2 of them are positive, 2 of them are negative, as we can see. Is the velocity positive or negative? Okay? Well, that matches because velocity is exactly the same as slope of tangent lines. So the first 2 are positive, the second 2 are negative. Okay? Now what about this idea of curved up or down? Okay? This is what I was hinting at just a second ago. Curvature. Okay? Well, what would you say? Well, A is curved up, B is curved down, C is curved down, and D is curved up. If you haven't heard a lot about curvature, the idea is think of a bowl. Positive curvature, up curvature, means that the bowl would hold water. Downward or negative curvature means the bowl's upside down and it would spill. Right? So this is negative curvature. These are positive curvature. If we imagine the curve continuing, like a parabola. Okay? All right, so now the tricky part. And this actually tells you, right, that the acceleration, so this would be positive acceleration, negative, positive, okay? Because the second derivative is curvature. All right, kind of quick note there, which is a whole rabbit hole in itself, but the second derivative of a function is its curvature. Since the second derivative of position is acceleration, acceleration is curvature of position. Okay, so what about velocity? Is velocity increasing or decreasing? Well, you look at A, and it's increasing, right? It's getting increasingly positive, okay? Look, what about B? Well, it's actually getting smaller, right? It starts off as some large value because it's the slope, right? So the slope is getting smaller. Maybe it was 5 here and 2 here. That's a decrease. Okay, that makes sense. So what about C? Well, you might say, well, C is getting steeper, but it's getting more negative. So if this original velocity is, say, -1, then over here, maybe it's -3. Well, is -3 smaller than -1? Of course. So C is decreasing. Likewise, D is increasing because even though it's getting less steep, it's approaching 0. So here maybe it was -3, but over here it's -1. Well, -1 is bigger than -3. So V2 is actually an increase. Why? Because we care about the sign. Why do we care about the sign? Because velocity is a vector. In this case, it's just a 1D vector. They can either point to the left or the right, or up or down, right? But it's still a vector. It has direction. But speed, well, speed is just the absolute value. So we get different results. Increasing for A, decreasing for B, because the magnitude is getting smaller. Increasing for C, it's more negative, but the magnitude is bigger. And D, decreasing. So this right here is a wonderful example of what is different between velocity and speed. Okay? All right. So now our final example involving antiderivatives and the end of this lecture. So the acceleration of a particle is found to be this. I give you the acceleration function. In the previous ones, I was always giving you the velocity function. Here you're actually given the acceleration function. It's linear, okay, but also has some initial value. Then I tell you that Vx equals 13 when t equals 0. That's your initial velocity. X equals 100 when t equals 0. There's your initial position. And that right there should tell you, well, if you've been given initial values, you're probably going to be asked for integrals. In other words, you're probably going to be asked to do antiderivatives. Okay? And then the question, what is the position of the particle after 1 second of motion? Well, sure enough, we have to work from acceleration to a position function. Let's do it. So first thing we're going to do is write our information here, our formula that says that the change in velocity is equal to the definite integral of acceleration with respect to time evaluated from 0 to t. All right, then we plug in 13. So notice what I'm doing here. Here, although the value was given here with the units, the function didn't have units in it. And that means I'm going to kind of stick with that notation because you see it both ways. Sometimes you see functions where it was very careful to put the correct units and coefficients. Other times it just looks more mathy and the units are left off. You have to be familiar or comfortable with both ways of presenting these types of functions, whether they're kinematic functions or force functions or whatever it may be. Okay, so I wanted to show you kind of both types that you might see. All right, so anyway, so then we're just plugging in, again, leaving off units. And let's go ahead and just follow this through. So I just do the rules of polynomials. I move the 13 over to the right-hand side. When I evaluate the 5, it just becomes 5t. When I evaluate the 4, it becomes 2t squared. Okay, just think rules of antiderivatives for polynomials. I mentioned it more in detail in the previous example. All right, so now we have our velocity function. That's cool. But we got to continue right on to our acceleration function. So we're going to take our result from our first step and just plug it into the integral. Okay, so we're going to do that. All right, so now we have a larger expression inside of our integral, which is of course just this. Okay, and I could have put the subscript there, v sub x. All right, and then we are just going to do the same thing, move the 100 over to the right-hand side, actually evaluate the integral from 0 to t. All right, and there we go. Now we have our full position function. Okay, notice that our acceleration function had 2 terms, our position function has 4 terms. Well, that's true for any time your initial position and initial velocity are non-zero, which they were. Okay, you gain terms proportional to the number of non-zero initial values. Okay, and then we just evaluate that at 1. So 100 plus 13 times 1 plus 2.5 times 1 squared. 1 is kind of boring because 1 to any power is just 1. And then 2/3 times 1 cubed. Once we do all that, we get 120. You might be like, hey, isn't it like 117 or 116? Yeah, but we only had 2 sig figs, so we got around to 120. Okay, so that concludes the last example. Not a super heavy lecture, but just a good introduction to actually, first of all, doing some calculus of kinematics, and second of all, introducing acceleration. Okay, so thank you so much for watching, and stay tuned for the last and final lecture video for this chapter, Chapter